Welcome to topic 1.7. This is our last topic in unit number 1. And in this topic, we are going to be talking about the different types of real numbers. So, taking a look at this chart here, this chart tells you all the definitions of all the different types of numbers we're going to be classifying in this section of notes. So our first type of number is a natural number. And a natural number is all positive whole numbers that don't have any decimals. Or in other words, natural numbers are counting numbers that don't include the number 0. Whole numbers are all natural numbers, including 0. And then integers are classified as any whole numbers and their opposites, meaning whole numbers and negative numbers. And integers also include 0 as well by definition. And our last two types of numbers are rational and irrational numbers. Now, rational numbers are going to be any decimals that do terminate, meaning decimals that have an ending point, or any decimals that repeat. So for example, like 0.33333 repeating, that's a rational number. And also, this definition isn't fully complete. A rational number is also any number that can be written as a fraction. So I'm going to say, or any number that can, or any fraction. And then an irrational number is a decimal that doesn't repeat or terminate. So, meaning a decimal that never ends, a decimal that goes out to infinity, and also any number that doesn't repeat. So, with that in mind, let's take a quick at this note here. So, any number that is a fraction, meaning a fraction is an integer numerator and an integer denominator, is always rational. And I saw that up here. So what this is saying is that any fraction is always rational. But the one thing to keep in mind is we all know, or we've heard of this thing called pi before. And we know that pi is a decimal that equals like something 3.14, and it goes on forever, right? And this decimal never ends. It does not terminate, and it has no sort of pattern, so it doesn't repeat anything. So we know that pi is an irrational number. But when you have an irrational number like pi, and you divide it by something like 4, this is technically not a fraction. Pi over 4 is technically not a fraction. And that is because you can't divide that is because you can't divide any rational number by a rational number and get out like a really concrete value, if that makes sense. Because pi is irrational and it never ends, you can get out an approximation, but because this approximation isn't like exact or somewhat close, it's considered not a fraction. So a fraction is, what's considered a fraction is anything that has two rational numbers being divided by each other. And rational numbers include these first three types of numbers here. So all these numbers up here are rational. And any other numbers that don't fit in with these categories or isn't a fraction, it's irrational. So let's just let's go look at some examples. So for example, number 1, we're going to classify all the numbers that we see, but also note that most numbers have multiple classifications. So looking at example number 1, we have the number 3. Well, the number 3, that's a positive whole number, and it's not 0, so number 3 is natural. Also, I'm just going to write out the first letter of these types of numbers. So N stands for natural, And 3 is also a whole number because it is included in our natural numbers. So 3 is a whole number. And 3 is also an integer because integers include all positive and negative numbers and 0. So 3 is an integer. And recall, anytime we have a natural whole or integer, it's also rational. And let me explain why. So in the previous section, when we were multiplying and dividing fractions, there was an example where you had like negative 10 divided by, I think it was like 15/12. Now we said negative 10, we can write that as negative 10 over 1 because it doesn't change the value. And negative 10 over 1, because both negative 10 and 1 are rational numbers, technically negative 10 and 1 is a fraction. So anything that's a whole number, anything that's natural, whole, or an integer is also rational. Taking a look at example number 2, we have negative 4. We have to be careful though because we're in the negatives now. So natural numbers don't include negatives. So natural numbers only include positive whole numbers. Whole numbers only include all natural numbers, which are positive and 0. But negative 4 is an integer because integers include negative numbers. So negative 4 is an integer, and it's also rational. Looking at example number 3, we have 1/2, which is equal to 0.5. While 0.5 isn't natural, whole, or an integer, but it is rational. And that is because it's a decimal that terminates or ends. Looking at 1/3, well, 1/3 is equal to 0.3 repeating. By the way, if you aren't familiar with this notation, in math, anytime you see a decimal with a bar like this above a number, that means that it's repeating. So this means 0.3 repeating. And repeating means this decimal repeats 3 infinitely. So it goes 0.33333333333 infinitely. So looking at our definitions, we know it's not a natural, whole number, or an integer. But we do know that it's a rational number. Why? That's because it repeats. All right. Looking at example number 5, we have the square root of 7. Now, the square root of 7, that's not a perfect square, right? Because we can't rewrite 7 as something squared, but we can write something as we can write 4 as 2 squared, which that would be a perfect number. But since the square root of 7 isn't a perfect number, if you were to put this in your calculator, you would get a decimal that doesn't follow any pattern. It never ends. It goes on infinitely. And because that is the case, the square root of 7 is just irrational. When a number is irrational, that means it can't be an integer, it can't be a whole number, can't be a natural number. And because it's irrational, it also can't be, or because it's irrational, it can't be rational. So whenever you have an irrational number, it's just irrational. There's nothing else by definition that it is. Looking at example 6, though, we have the square root of 9. Now, square root of 9 is not irrational, and here's why. Because the square root of 9, that evaluates to 3, because we can rewrite 9 as 3 squared, right? And we know that the square root is the opposite of something squared, so the square root of 9 just equals 3. And 3, well, 3 is a natural number. It's a whole number. It's an integer. And it's also rational. And we also already defined what 3 is on this first example here. So that's one thing to be careful of. Just because something has a square root doesn't automatically mean that it's irrational, because we do have perfect squares, or square roots that evaluate into a perfect number. For example, number 7, we have pi. Now, as we discussed on the first page, pi is an irrational number because it's a decimal that goes on forever, 3.1415, and I don't know the other decimal places, but it goes on forever. And it never ends and doesn't have any pattern, so it's irrational. Now, 0. Let's take a look at our definitions. So, according to our definitions, a natural number does not include 0, but whole numbers include 0, integers include 0, and because it's a whole number and an integer, it's also rational. So 0 is a whole, integer, and a rational number. So we have whole, integer, and a rational number. Looking at example 9, we have 4.5, which that's not a natural, whole, or an integer, but it is rational. And that is because the decimal terminates, the decimal ends. It has an ending point. We can vividly see the ending point is 4.5. Now looking at our last example, example number 10, we have 4 plus the square root of 2. Now 4 happens to be everything that 3 is. It's a natural number, it's a whole number, it's an integer, and it's rational. But because we are adding the square root of 2, which is a decimal, if you evaluate the square root of 2 in your calculator, you get out a decimal that goes on forever. There's no certain pattern. It doesn't end. Because you're adding an irrational number to a rational number, this becomes irrational, this whole expression. Even though 4 is rational, if you add an irrational number to it, you are adding an infinite decimal. So that becomes irrational. Alrighty. Looking at our example type 2, we're going to be given a statement, and we're going to have to decide if that statement is always true, if it's sometimes true. For example, if there's a case where the statement would be true and there could be a case that the statement is false, or if the statement is just completely false and it's never true. And then we're going to have to justify what we were saying by giving some examples. So let's work through it. So for example number 1, we have the statement, a fraction can be an irrational number. And this one can be a little tricky sometimes. And this one happens to be never true. And here's why. Because a fraction, by definition, must have an integer numerator and an integer denominator. A fraction bar represents division, but division alone does not guarantee that a number is a fraction, right? So by definition, an irrational number is not a fraction. And I established that up here, and that's why I said my definition is not fully complete, because any fraction is technically a rational number. Looking at example number 2, I encourage you to pause the video and try this one on your own. And assuming you have given it a go, let's work through it. So for example number 2, we have the statement, an integer is a natural number. Now, this statement is sometimes true. There are cases when it can be true, and there are cases when this would be false. Let's work through it. So I'm going to first show some examples of when this would be true. So in this example, this would be true if we have an integer that's 1, 2, 3, 4, and so on, right? Any integer that's a natural number. So any integer that's a counting number, this statement would be true. But this is where the statement becomes false. Anytime we have an integer that's 0, -1, -2, -3, and going forever into our negative numbers, that's when the statement becomes false. So the statement is sometimes true. Looking at example number 3, I encourage you to pause the video and try this one on your own. Now let's work through it together. So the statement is a square root is an irrational number. So this statement is also sometimes true. Sometimes true. So the statement is true when we have a square root that doesn't evaluate to a perfect number. So we have 2, for example, square root of 5, square root of 7, let's say square root of 12, and so on. So anytime we have a square root that doesn't evaluate into a perfect number, it is irrational. But then you also have some square roots that evaluate to perfect numbers. So for example, the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, square root of 9 is 3, and so on. Alrighty, and for example, number 4, we have the statement, an irrational number can be written as a fraction. Now, I encourage you to pause the video and try this one on your own. And I did give the answer to this statement a couple times throughout the video. So I encourage you to go through the video and see if you can find the answer. And assuming you have given it a go, let's work through it. This statement, an irrational number can be written as a fraction, is never true. And recall that's because irrational numbers can't be written as a fraction. So, for example, as I stated before, something like pi over 4 is technically not a fraction. Now, it does have a division bar, but the division bar alone doesn't mean that you technically have a fraction. So that's why this statement is never true, because an irrational number, by definition, can't be written as a fraction. So anytime you have a fraction, it's not irrational. So that's why this is never true. Looking at example number 5, we have the statement, a repeating decimal is an irrational number. This one is never true. And that is because, by definition, a repeating decimal is a rational number. Looking at example number 6, our last example, I encourage you to pause the video and give this one a go. And assuming you have tried this example on your own, let's work through it. So we have the statement, an integer is a rational number. So is this always true, sometimes true, or never true? Is an integer always a rational number? This statement is always true. Because any rational number can be written, or any integer can be written as a fraction, as we have seen. Alrighty, and that concludes Unit 1. Thank you, and I can't wait to see you for Unit 2.